As the next theorem, we have squeeze theorem. Assume you have an fx function which is between gx and hx function. In this case, when limit of gx is L and limit of hx is L, then you must say that limit of fx is squeezed between those two L values, so it must also go to L. So this is our squeeze theorem, and we have a classic example here. For example, limit when x goes to 0, we need to find the limit of this function sinus 1 over x squared times sinus 1 over x. So in this function, we already know what is squeezing, between which values are oscillating sinus 1 over x. So if sinus 1 over x is oscillating between minus 1 and plus 1. So we have already some functions. This is like a gx function. Here, when you take this as an example, this is like an hx function. Plus one is like an hx function, and this is like an fx function. Here, not fx, but let's say cx function here. So this cx function is between minus one and one, gx and hx. So when you multiply, but we are looking for the when x goes to 0, x squared times sine x divide sine 1 over x. So we have sine x, sine 1 over x here, so we need to multiply both sides, all sides with the x squared, sorry, minus x squared smaller than equal to x squared sinus 1 over x smaller than equal to x squared. So we have here in this function. So when limit x goes to 0, we are looking for x squared times sinus 1 over x. So here, when limit x goes to 0, this is going to 0. So this is also going to 0. That is why this must go to 0. This is the squeeze theorem. From left side, we are going to 0. From right side, we are going to 0. That's why the function in the middle must also go to 0 when x goes to 0. We, we could have another example, such as when limit x goes to 0, x to the 4th times cosine, for example, 1 over x square, 1 over x square. So here we already know that cosine 1 over x square is between minus 1 and 1. So that's why 1 over x square between 1. We are doing just same example. So we know that this is between minus 1 and 1. We need to multiply all sides with the x to the power of 4. So minus x to the power of 4 smaller than equal to x to the power of 4 cosine 1 over x square smaller than equal to x to the power of 4. So when limit x goes to 0, this is going to 0, this is going to 0. So this must also go to 0, which is the answer for this problem. And for this one is also 0. Okay, for the intermediate value theorem, if assuming that f is continuous between a and b and a and b x values, and we have f a and fb in comparison to this a and b x values, and there is an n between fa and fb, there must be a c between a and b such that fc equals n, and c is between a and b according to intermediate value theorem. So if f is continuous, this is important. If f is continuous on a and b, so continuity means you must draw function without moving your hand, without you moving your pen to another side directly. You must continuously draw that function, and you have, for example, a here, b here, fa, and fb. This function is continuous. We can give any value between a and b as an input parameter, and it will have a corresponding y value. And and all values have corresponding y values, and their limits are also equal to the corresponding y values for those x values between a and b. So you have, for example, n here. If n is between fa and fb, there must be a c between a and b such that fc equals n. So we have c. This is intermediate value theorem. But here the important part is f must be continuous on a and b. So you cannot have, for example, you cannot have a value such here. You cannot have a value such that you have, for example, n1 and c1. You cannot have, if c1 is between, if c1 is between a and b, then this N1 must also be between FA and FB. Because if C1 here and N1 here also, so and if we say that both the function is continuous and this is true, then there is a jump here. You are drawing your function here, and up to point, you cannot say this value is true. You are saying that this n1 value is true. So you have a field circle here and you have an empty circle here. So that means there is a jump here. But you cannot have a jump. That jump makes the function discontinuous. But at the beginning you have already said this function is continuous between a and b. Or you cannot have a value. For example, you have n value here, c value here. You cannot have something like c2 here. So this is also making this also makes the function discontinuous, because you have empty circle here, and this C2 value is satisfying n value. You are saying this C2 value is satisfying n value here, not the C itself. So here you will be having an empty circle, which makes the function again discontinuous. But at the beginning you say f is continuous. So you are contradicting yourself with the first rule of view. So that's why this type of drawings cannot be done. So we are using those functions as a root of in order to find the root existence. For example, we have fx equals x to the cube plus x minus 1. We have f0 minus 1 and f1 equals 1. So in this example, we have if f is continuous between 0 and 1. So these are like a and b here. F is continuous between 0 and 1. And we have an fa here, which is minus 1. And fb here, which is 1. Fa and fb here, which is minus 1 and 1. We need to check whether there is a c such that c is root of this function and c is between 0 and 1. So according to intermediate value theorem, if we have minus 1 and 1 and we are checking the root of this function, which is 0, is 0 between, 0 is our n number here, is 0 between, which is the root of this function, is between minus 1 and 1. Yes, not the root of this function, but the value for this function. Uh, is 0 between minus 1 and 1? This must be equal to 0. Yes, 0 is between minus 1 and 1. So there must be a c value. There must be a c value such that fc equals, fc being our root, equals 0, and c must be between 0 and 1. Why? Because when you give fc, it is our root. Since it is our root, the y value is 0, and y value 0 is between minus and 1, minus and 1. So if 0 is between minus and 1, so that c value must also be between 0 and 1. So there is a root exist. So limits involving absolute values. For the absolute values, we need to have, uh, we need to, in order to get rid of these absolute values, we need to use, we need to access approach to x from right or left side. If you approach from x from the right side, and this x absolute value, since we are using values greater than 0, this is just behaving like x, and x over x is 1. If we approach x from the left side, this is when you, since it is negative, when you get rid of these absolute values, you must put minus x divided by x, and this is why it is minus 1. So when you involve the functions having absolute values, you need to take care of sign of the x, so that you can correctly get rid of these absolute values. For the values small, if x is positive number, you can just get rid of absolute signs, and you can just write it as. And for the values smaller than 0, you cannot write it as is inside, as it is inside the absolute values, you must multiply it with minus 1. That's why when x goes to infinity, so when x goes to 0 from right side it's 1, when x goes to 0 from left side it's minus 1, and limit does not exist. When x goes to 0, absolute value of x divided by x does not exist, since the right side of the limit and left side of the limit, they are not equal to each other, doesn't exist. For the limits involving composition of functions, you can we have two, assuming that we have two functions and outside we need to take the limit of those functions. You can just reverse the order of limit and outside function, and you can just write it as f. First, take the limit of gx and take the f. Here we have fog, simply fog x. F is taking gx as parameter. We are calculating that, then we are taking the limit. But this can be rewritten as first take the limit of gx according to a, then calculate the fa. So these ordering can change, and you can just take the limit of the inside function, and then according to that value you can calculate the f. So here we have examples: limit x goes to 0, sine x square plus 1. This sine x is like fx here, and x square plus 1 is like gx here. So sine x and limit can change the order. Sine limit x goes to 0, x square plus 1. So limit x goes to 0, x square plus 1 is going to 1. This is sine 1. And here also we can do the certain change here. Ln limit x goes to 2, x square plus 1. Again, limit x goes to 2, x square plus 1 is going to 5. Here is 5, and you have ln function ln 5. ln 5. If your function involves the square root, if you have a square root of x square, for example, here normally you can get rid of this, but and you can just write x. But for the limit cases, when we are talking about limits, you cannot do this. In order to get rid of square root with the square, you must put an absolute value here. That's why signature of x matters. For the x greater than 0, when x goes to infinity, this is behaving just like x. For the values smaller than 0, this x, absolute value of x, is behaving like minus x. That's why the sign matters. We have an example here: when x goes to infinity, 9x square plus 1 divided by x. So this is when x goes to infinity, 3x square can be rewritten as 3x square plus 1 divided by x. So when you get rid of those, you will end up with 3x plus 1 plus x. So it is going to infinity. That's why you can just get rid of those absolute values, and you can just, when x goes to infinity, you have 3x here. You got rid of those absolute values, absolute signs, and when x goes to infinity, you have exponential being 1, exponential being 1, and coefficient of this 1, coefficients of this 3. You can just write 3. For the when limit x goes to minus infinity, again 9x, again same function. You have 3x squared plus 1 divided by x, which is 3x plus 1 divided by x. So x is going to minus infinity. That is why this is behaving like minus 3x plus 1 divided by x. So you have minus 3 over 1, minus 3 here, and 3 here. That's all I can describe about the limits and the rules of the limits, and we have done some examples related to those rules and theorems. We have learned vertical and horizontal asymptotes, limits at infinity and infinite limits, etc. So I hope you enjoyed the video. Until next time.